Hello and welcome back. And in this video, we are going to discuss about the Python code sample for the interaction terms. So this is the piece of code that I have, and I will explain you these things, like whatever has been written in the code. So let me first import all these libraries. So let me open my, yeah, this is the Jupyter notebook. So here I am just importing import pandas and stat model.api. So this is another library that you must need to install. So you can do pip install just like I have done probably here. Yeah, this is the one. So I have done pip install stats models. So you can run this and you will be able to install all these functions, objects that are available in the library. So this library will be installed for you. So this is needed. So run this pip install. Just you can see this pip install stats models. That's it. You run it through the command prompt and then you come back to the Jupyter notebook. So let me run it. Here you go. So it is fine here. Every library is already imported. Stats models is also imported. So now we can move to the next section, which is the sample data. So in this sample data, what we are doing, we are preparing the data here. X1, X2, Y. So X1, X2, these are the two features and Y is the resultant. The dependent variable. X1 and X2 are the independent variables, basically, which are the features. And now this data frame, you already know. With the help of this data frame, we have to just load the data into the variable df, right? Let us print the df as well to see how it looks like. So let me run it. So here you go. So here it is, the data, which will look like something like a matrix. Okay. So 0, 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, 2, 4, 6, 8, 10, and then 3, 8, 15, 24, and 35. So this is how the x1, x2, y, these values have been distributed, or sorry, have been loaded into the data frame. Okay, so let me remove it, run it again, and let's go to the next section, which is the creation of the interaction terms. So we are going to create the interaction terms here. Okay, so you can, just stop the video and you can write the code yourself. I will not provide you in the comment or description section because you can copy and paste these. But the thing is that if you copy and paste these, then you are not writing your code yourself. So basically, it will be good if you write your own code yourself. So here we are creating the interaction terms. So x1 and x2, they are the kind of variables which are interdependent on each other. So df x1 x2 is equal to df x1 into df x2. So this is how we are creating the interaction terms. Okay, so we are going to create this thing, interaction terms. So after interaction terms, we are going to fit the regression model. So till here, I'm just going to copy and paste. So here we go. So we are creating the interaction terms here, multiplying the two variables, right? Because the two of the interaction terms have the multiplier effect. So we are multiplying it and then fit the regression model with interaction terms. Okay, so here we go. X is equal to df x1 x2 x1 into x2, and then x is equal to sm dot add constants x, and then we have called this OLS method. Okay, so let us see what does this do. Okay, so what we are doing in this line, add constants. Okay, so here we are preparing our model, like with the help of the x1 x2 and x1 x2, we are creating the kind of set of variables into this x, right, which are dependent on these x1 x2 and the interaction term x1 into x2. Okay, so let me just print it, print x. Okay, and let's first see what does it look like, and then just add a comment and then run it. Here you go. So how it looks like, x1 x2 1 and 2, then multiplication 1 2, 1 2s are 2, 2 4s are 8, and 3 6 are 18. So you can see we have created the matrix with the help of the x1 x2 interaction terms along with x1 and x2 as a separate feature. Here you could see that this was when we just printed it, it was x1, x2, and y. But here we are just working on the independent variables. Okay, so x1, x2, this is simply we have just prepared in here. So let me just remove it and let's see the next thing, which is x is equal to add constants. So let me first remove it and then let's see what does it do, right? So add constants. What is the output after the add constants? What we are doing? Okay. So let me print it. Print x. So here you can see the constant which has been added is 1.0. So the constant has been added. So add constants. What does it do? So let's see. What does it do? Let me copy it. So let me. What does the add constant add underscore constant method do? Method of does. Okay, do. So let's see. So this is Gemini. You can simply go through the Gemini, which is free, and then you can use the free version to ask any of these questions. You don't need to go anywhere else. You just ask it to explain it in the simplest terms, and it will explain it for you. So add constants method is a stat model is used to add a column of one to a given data set. This column represents the intercept terms in statistical model, specifically in linear regression models. Why this is necessary? Right? So here it has been mentioned. So like the interaction term beta 0 represents the value of y when all independent variables are 0. By adding a column of 1 to the data set, we essentially introduce a new variable that takes on the value of 1 for each observation. This allows the model to estimate the intercept terms along with the coefficients for the other independent variables. So this is just the error term that could be there. So that error term has been added, and basically based on that, the intercept on the y-axis, because this is simply a linear equation, right? So in case of linear regression, if you have linear, model, then in that case, a linear equation creates a line, and that line is obviously going to cut somewhere at the y-axis. So the intercept on the y-axis, that for that the error term is calculated here. Okay, so this also calculates the coefficient for the other independent variables. Okay, and then comes the other method, OLS. So let us ask this one. What does OLS method do in this one? Okay, let's see. Ordinary least squares method. Okay, so this you can read. What does it mean? The ordinary least square method in stats model is a statistical technique used to estimate the parameters of a linear regression model. It works by minimizing the sum of the square residuals, which are the differences between the observed values and the predicted values for the model. So basically what is happening that it's just calculating the difference between the square of the difference between the observed values, whatever we have observed, and the predicted value. Whatever we are, we have the predicted value and whatever we have observed, right? Observed means whatever is there in your data set. Okay, whatever data set provides that for the y or for the output variable, that is the observed value. But whatever your model will be predicting, based on the understanding, that value is known as the predicted value. So the difference between the observed value, which is the value from the data set, and the predicted value, which will come after the training of the data set for the model, right? After the training of the model on the data set, whatever value it will be predicting, the difference between the two and their square, the square of the difference, that will be taken, and based on that, it is able to decide that how I need to fit my model, how fit my model is, and based on that, it keep doing regression. Okay, so you can read about it in the details. You can ask the question, and simply it will give you all the details about the functions. If this was related to the, libraries of the Python, uh, then I could have explained it in more detail. But yeah, I know that you will be able to understand it, and this course is not for the explanation of these kind of methods, but it's all about the feature engineering mostly. So I will be stick to the example and its basic understanding. Okay, so let us go to this point, and let me just remove it, print x, and then let us fit it, sm.ols, this ols method, ordinary least square methods. Let me run it. And after that, if you want to print, it has been successfully executed. If you want to see what does model look like, then you can write like model. Maybe it will just give you the address. Yeah, it is just giving you the address at the particular location in the memory where this model has been saved. And if you want, you can simply save these models right into your uh, local directory so that you can reutilize later on. So sm.ols, this is the one where you are fitting the data, which is in X, and you are giving the data set F, I mean, the value of Y you are giving here, which is the output variable. So against the output variable, you are training it, and based on that, it will be containing the model which will be predicting data based on the unseen data. Whatever data you will be providing based on that, and based on the training that it has done on this data, it will be giving you the results. So let us go to the next one. The next thing is that print the summary model. So we are going to print the summary after fitting the data. So we are going to print the summary. So let me run it again and then print the summary. So if I print it, so it is printing the summary. So you can see this is the summary. After OLS regression results, it is giving you the notes, right? So you can understand these things. Like, I'm not going to explain this result, but yeah, if you want me to explain this, then I would like to explain it in the next video, or maybe you know in in the coming videos, because these things we will keep working on, and somewhere OLS we are again going to use. Okay, so if you want it like how I should explain it, then I will explain it. Otherwise, you will be able to easily understand it. Again, your tool is like Gemini or any large language model for that matter. So you can use any large language model, and you can simply put it there, and you can find out like what does this OLS regression results means, and how to read it, and what should I interpret from it. Okay, so these are the notes. Standard errors assume that the covariance matrix of the errors is correctly specified. The smallest eigenvalue is 1 point. This might indicate that there are strong multicollinearity problems, or that the design matrix is singular. So this is showing some kind of problem. It is showing that this model may not be that effective. These notes are important. So once these notes are here, you can understand that yes, there are some problems, right? So this note indicates that there is some problem. But yeah, but whatever we are understanding here, whatever data we are using, that is a really a very small set. So these kind of things can come. My whole purpose is that I should be able to explain this piece of code to you. Okay. And let's go to the next piece of code, visualize the interaction effect. We are going to visualize it. Okay. So let me put all the things in here. Okay. So here, fix x2 at two different values, 2 and 8, and create a range of x1 values. So we are creating a range of values which is 0, 10, and 100. What does this line space method do? It creates, just like here we have written like 0, 10, 100. So it is creating 100 records, 100 random records for us. And those records, each of the value in those records will be separated with an interval of 10. That's how it will be working. So let me just print it for you so that you can understand it. Print x1 underscore range. So if I print it, if you see here, this is how it will be, giving it to you, right? So here it is giving you the values. So 100 records it has generated for you between 0 to 10. Sorry, between 0 to 10. This is the initial value, this is the final value. So between 0 to 10, 100 records will be generated, and those records will be some real numbers. Why we are generating? Because we don't have the real data. That's why we are creating a range of data. Okay. So between 0 to 10, it will be generating 100 records. Okay. And, it will be generating the records in such a manner that the difference between the two records is equal, right? It's not 10, it's equal, right? It may be anything, whatever it could decide, it can decide and it can simply put that value. Okay. So this is how we have done this. And this is the fixed value. Okay, so this is the fixed value where we are putting like 2 and 8. These are the fixed values. What do you mean by the fixed values? The fixed values are like for the beta 1 and beta 2, whatever you want to fix, that is the fixed value, right? So here we are going to put it here. So beta 0, x range, and then fixed values. So beta 2 fixed value, the first one we are taking as the beta 2 fixed value. Here it is. So we are multiplying it by 2. And here for the beta 3, I mean for the x1 into x2, where we are multiplying the two interaction terms, two terms, there we are taking again it as 2. I mean, first time we are taking it as, you know, the fixed value as 2. And in the next one, we have taken the fixed value as 8, right? So y predicted 1 and y predicted 2. So there are two predicted set of values we are preparing here. Okay, so for y predicted 1 and y predicted 2, we have taken two fixed values, right? To make my data set and training set more robust. Okay, so here what we are doing, we are creating y prediction 1 and y prediction 2. And based on this, we can see that how does it look like. So let me print y underscore pred underscore 1 and then print y underscore pred underscore 2. So let's see what does it print. So it is printing two values. Okay, so the values in the y, whatever y values are there, 3, 8, 15, 24, 35, those values have been manipulated. Wow. So after multiplying it with y2, it has created a range of 7 to 17. Between 7 to 17, it has generated the values. And similarly, y2 has generated between 25 to 5. Okay, so this is how it has generated the data. Okay, so here you can see it is decreasing between 25 to 5. So two things it has generated. So here if you see 2 to 8, there are two values 2 and 8. One is fixed at 2, the other one is fixed at 2. Sorry, 8. So the one which has fixed at 2, we have used it here. Fixed terms, we have used it here, the first value. And the fixed term, we have used it here as well with the second value, which is 8, right? So to create a diversity in the predicted values, we are doing this. So let me just remove this thing. Let me run it. And then let's come to the other one, which is plot the interaction effect. So we are going to plot the interaction effect. So let us see how does it look like. So plot the interaction effect. So with y prediction 1 and y prediction 2, with both we are just going to print it. Okay, so x2 is equal to 2, x2 is equal to 8. The same thing we are doing. Label, when the label is x2 is equal to 2, I mean that labels will be shown in the graph, and they will indicate that what will be the graph plotted when we have taken x2 or the fixed value as 2, and what will be the graph looking like when we have taken the x2 as the 8. So here we are going to provide the x label, which is x1, and the y label y, and then we are adding the legends, which are labels that we have given here, and then we are showing it. So let us see how does it look like. So here it looks like, so x2 is equal to 2. So this one, which is in this color, kind of blue, so this blue color line is showing the performance when we are using the term, I mean the fixed term as 2, fixed value as the 2. So on fixed value 2, this will be the graph. This is the ideal line. This line, or you can say the equation of this line, Or you can say for this line, whatever beta 1, beta 2, beta 1 into, beta 1, beta 2, and beta 3 values along with the intercept will be there. That will be the ideal line for prediction. That equation will give you the ideal line for the prediction. Similarly, for this one, this can also be used for the prediction. This line can also be used for the prediction. So whatever line it will be, whatever line it will be, I mean, if you see here, this is y is equal to beta 0 plus beta 1 into beta plus beta 2 plus beta 3 into some values, right? So this is representing some kind of line, some kind of curve. So based on that curve, what will be the best fitted curve when we are taking this y prediction one? What will be the best fitted curve and the equation for that curve, right? What will be the values of beta 0, beta 1, beta 2, and beta 3 for this line? That will decide your this this function y is equal to whatever you are taking, right? So these values will decide what is the line equation, and based on that you will be able to predict the different values on the unseen data. When you are going to test your unseen data, then in that case, the equation of this line will help you to predict the values. So this is the ideal line to predict the value. That is what something we are going to understand here. Okay. So I hope you must have understood this. And I would say that I must say that you should write the code your own by stopping my videos. You can keep writing, you can keep understanding the code, piece of code, and then you will be able to understand that how and what way we should be able to prepare a model. So here you have seen that how the interaction terms play a role and how you can decide and how you can find out a particular model or a particular equation, the prediction value, how you can find it out, right? And based on that, you can decide based on the unseen data that what should be the predicted value for an unseen data. So with this, I would like to say have a nice day and bye bye. We'll meet soon again. Till then, have a nice day.